last time, the last structure we have defined several examples or several kind of ring structures. So also I have given you an exercise for that. What will be the intersection of, yeah, units intersection the idempotence, right? So this will be precisely one. You can easily verify. Okay, it is easy to check that this is going to be one, right? So now I am going to prove, today I am going to prove that set of all units as a group under the second binary operation, right? So I will prove this is a proposition actually. So u of r, that is units in r, with respect to second binary operation, that is the multiplication, is a group, where r is a ring with unity, right? R is a ring with unity. Okay, so R is a ring with unity, then UR, that means the units of R with respect to the second binary operation is going to be a group. How do we check some structure is a group? So we always prefer by the definition. So how do we show this is a group? This should satisfy the property or associativity, the closure property, that associativity, then existence of identity element, and existence of inverse element. That's what we call a group, right? So how do you show this is a group? Is it a binary operation? So first of all, you should show the set is a non-empty set. So r plus is a ring with r plus dot is a ring with unity, so there exists an one r inside. So r plus dot b is a ring with unity, is, so my my handwriting is very bad, so please pardon me for that, right? So you just manage it. So r plus dot is a ring with unity, so this implies, so there exists a one r inside the ring r, just that, and 1r dot 1 r, this is equals to 1r. This implies that the ring, the units is non-empty, because 1 itself a unit, right? So this is a non-empty set. Now you should closure property. How do you show this is a closure property? Suppose that a comma b is a member of units. Okay, so it this means, what does it mean? This means that there exists a c comma d inside the ring r, just that ac equals to 1 r, and bd, this is equals to 1 r, because of a and b are two units, so there exists some c and d, such that this happens, right? So my claim is ab should be inside. My claim is ab should inside. AB is also an unit, right? So how do you show AB as an unit? So what you have initially is, so you have, let me check, A, B, D, C. What is it? What is this is actually A, and what is BD? BD is 1R, and C, this is A 1R dot C is actually C. This is actually 1R. A dot C is 1R. That's it, right? So for AB there is a DC, right? So for AB, so AB inverse is actually DC. For AB there exists DC, this element. So this implies that AB is also an unit, right? So this implies that AB is inside. You are right, is it? So check for the identity. Check for the inverse. Identity is 1R. 1R is identity. It is pretty clear, identity. And what will be the inverse? So associativity is left, right? So associativity is very easy to show. This is associativity, and inverse. You can see that if A is a unit, in R, then there exists B, then there exists B inside R, such that AB this is equals to 1 R, this is equals to BA, right? So this implies that A inverse equals to B, which is inside UR. That means B is also an unit, right? So for B there is A inverse, that's what, right? So inverse and associativity, inverse, everything is sorted out. So now you can say that UR, this is a group, right? So this is a group. So now, so I'm giving you some structures, right? C, complex numbers plus dot is a ring with unity, is a ring with unity, right? Is a ring with unity 1R, which is actually 1, So what are the units in C? This is actually all those complex numbers Z inside C, such that Z dot A, this is equals to 1 for some A inside C, right? What's that? This is actually Z, sorry, this is C minus 0. Every non-zero element is an unit, right? So all similarly for Q plus dot is Q minus 0, and R plus dot, this is also R, this is R minus 0. Every non-zero element is a unit. Similarly for U of Z is actually it is plus minus 1, right? So these are some every non-zero element is a unit, right? So now you are in a situation that you have some ring, okay? You don't have so many rings, but you have some ring, so you know the structures of them, right? So what is the definition? What was the definition of zero divisor I have given in earlier? So the definition actually says that, so I'll show that a zero divisor cannot be an unit. What is the definition of zero divisor? Let me write first. Zero divisor, I am writing in very short, right? Zero divisor. If I'm going very fast, then please let me know. I will try to make it more precise. So let R plus be a ring. Actually, I am not interested in writing something. So let R plus dot be a ring, and an element A which is non-zero is called a zero divisor if there exists B which is this is also non-zero inside R, such that AB this is 0 or BA is 0. BA this is 0, right? So then we say that A is a zero divisor or B is a zero divisor. So let it possible A is a zero divisor. I will show A cannot be an unit. Let it possible, suppose A is an unit, right? Let us suppose A is a unit. I will show A cannot be a zero divisor. What does it mean? This means that there exists B inside the ring R, such that A dot B this is equals to 1R, or B dot A this is equals to 1R. Okay, so let it possible A is zero divisor also. Suppose A is a unit. So first of all I have assumed. Let us suppose I am assuming that A is also zero divisor. Let's see what happens. So what does it mean? This means that there exists C which is non-zero inside R, right? Just that A dot C this is equals to 0. What does it mean? You multiply by B. B A C, this is B into 0 which is actually 0. What does it mean? What is BA? BA is 1. So 1, this is 1 dot C, this is equal to 0. This implies the C is equal to 0. I have assumed the C is non-zero here. I'm getting a contradiction to the fact that C is 0. So this is going to be a contradiction to the fact that C is non-zero. So A is a zero divisor. So if A is an unit, so A cannot be a zero divisor, right? So I'm writing a statement here, sorry. A unit cannot be a zero divisor. Maybe this color is not suitable for me. A unit cannot be a zero divisor. Okay, a unit cannot be a zero divisor. This is not possible. Here I have am I clear with the proof? I think you should clear. This is very easy and very trivial proof. So that's it. So let me define some more properties and some important yeah, this statement is very very important. Okay, also I am proving a statement here. So what is this statement actually says? That if you are in a finite commutative ring with unity, then every non-zero element is either a unit or a zero divisor. It cannot be any other except this two, right? So in a finite commutative ring with unity, write the statement. The proposition you can write is, so in a finite commutative ring in a finite CRU, every non-zero element is either a unit or a zero divisor. How do you show? Proof. Every statement I will give the proof. I will not give any statement without proof. Okay, so there is a logic behind every statement, right? So without logic, if you studying only logic, only the statements, you will not be able to see. So without any proof, I will not give you any single statement here, right? So in a finite commutative ring with unity, every non-zero element is either a unit or a zero divisor. How do you show? So this proof is also very easy proof. So let R be a finite commutative ring with unity. Suppose this R is a finite CRU. For any A, fix a non-zero, define a function f from R to R. R means the ring R, okay? And how do we define? X goes to AX. That means actually f of x. This is x, right? F of x goes to AX, right? So what are the choices for f? So f can be 1 1, or f can be 1 1, or f cannot be 1 1. There is two choice. Suppose f is either 1 1, so there is a possibility. So f is either 1 1 or not 1 1. So if you have a map, so maybe it is 1 1 or maybe it is not 1 1. There is two choice. It may be 1 1, it may not be 1 1. So suppose if f is not 1 1, suppose f is not 1 1, case 1, suppose f is not 1 1. So suppose f is not 1, so what will happen here? So if f is not 1 1, so there exists x comma y and they are distinct. X is not equals to y inside the ring R, such that fx equals to fy. It means that f is not 1 1, right? So the two different images have two different elements have the same image, right? This is you mean by 1 1. So it means that ax equals to ay. It means that a into x minus y, this is 0. So a is non-zero element and x and y are not equal, so this is non-zero element. So this is not 0, this is not 0. Okay, what does it mean? Two non-zero element give me 0. That means that A is a zero divisor. Okay, so if F is not 1 1, then A is a zero divisor. Okay, so case 2, F is 1 1. This means that F is on 2, because of F is R is finite. If it is finite, so if F is 1 1, then F must have to be on 2. It's very trivial things. So on 2 means, this implies there exists X inside the ring R, such that Fx, this is equals to 1, because this is a finite commutative ring with unity. There is 1 inside the ring, so every element should have a pre-image. So there exists R as a codomain such that Fx equals to R, 1R, right? It means that Ax, this is equals to 1R. This means that A is a unit. Basically, it does not mean, it means that Ax equals to 1R. What does it mean? This means that A is a unit, yeah? There exists X. For A, there is a X. Okay? So easy. So in a finite commutative ring with unity, every non-zero element is either a unit or a zero divisor. Okay? So am I clear with the statement? In a finite, this is important here, finite, right? In a finite commutative ring with unity, every non-zero element is either a unit or a zero divisor. There is no other choice. Okay, so the proof is very easy, I guess. So what else I should do here? Okay, so there is one more thing I should have to prove here. So a finite integral domain is a field. ID, I'm just writing in short, ID is a field. I think this is very easy. This proof is also very easy. So this is, there is no mathematical expression here. You can prove by an argument what I have given just. So if I have an integral domain which is finite, so this is going to be a field. What is the definition of a field? First of all, a commutative division ring is called a field. What is the division ring? A ring with unity in which every non-zero element is a unit, right? So I guess I don't have to say anything more. This is very clear. Okay, so let me set up the situation. Yeah, okay, let R be a finite integral domain. What is the integral domain mean? Integral domain means this is a commutative ring with unity without zero divisor. So integral domain, this implies that R is CRU without zero divisor. There is no zero divisor, right? So finite CRU units of every non-zero element is a unit. So R is okay, there is finite, right? Finite CRU in which every non-zero element is an unit, because an element is every non-zero element either a zero divisor or a unit, because since it is not a zero divisor, so it should be an unit, right? So and commutative division ring is called a field. So this is called every non-zero element is a unit, and this is CRU. This implies that R is a field, because you have a ring with commutative ring with unity in which every non-zero element is a unit, right? Here every non-zero element is an unit, so this implies that R is a field. The commutative division ring is called a field, And what is it mean by a division ring? Division means that so ring with unity in which every non-zero element is an unit. So that's it, right? So this is also over. So now I'm going to analyze that. I think this is, there is no need to analyze that Zm. You have Zm addition modulo m, multiplication modulo m. Do I need to analyze this ring? Because you know everything about, I guess, this ring. So let me just give an overview. Okay, I will give just an overview, right? So this is a finite zero, you know. First of all, this is a finite commutative ring with unity. Finite commutative ring with unity, right? There is one, of course. So what are the units? What are the units? Units of Zm. This is, I am saying that this is all those natural number such that the GCD of k comma m is 1 and k is less than or equals to m. Okay, suppose this is called um. Say why these units are all only this, all those natural numbers such that the GCD with m is 1. Why this is so? I will show. Actually this is nothing but how many elements are there? This is actually u of Zm. The cardinal is actually phi m. This is the definition of phi function, right? Euler's torsion function, right? So this is phi m. Also, so I will show that this set is, this is the units, and actually these are the units, only units are this. So I will show that, suppose that I will show that this is a subset of this and this is a subset of this. I will be done. Suppose x be an element of, let x be an element of u of Zm, right? What does it mean? That means there x is a unit. That means that there exists a inside Zm, just that x a, this is 1, this is congruent to 1 mod m, right? 1 mod m, right? So also you can write m dot 1, this is actually m, this is congruent to 0 mod m. This is because this is, you are in all in Zm, right? So m is congruent to m mod, or whether m is congruent to 0 mod m, this is right. And x is congruent to x is 1, that means 1 mod m. Because of x is an unit, so there must be an 1 a inside Zm such that x a is congruent to 1 mod m, right? And also m dot 1 is m, which is 0 mod m, right? So I am adding this two. So from here and here, what do we get? I get x a plus m1 is congruent to 1 mod m. This is basic number theory. This means that the GCD of x comma m is 1, because I can write x and m as a linear combination. Okay, so this means that x is an element of the set whatever I have assumed um. This means that u of Zm is contained in um. Okay, and similarly you can show that this set is also under here. You can it is very easy to verify that this, I am giving you a little hint here, for the reverse part, right? Reverse part. So reverse means the other inequality. So let a be an um. What does it mean that GCD of a comma m is 1, right? And a is less than or equals to m, right? So GCD 1, what does it mean? dA plus ml, this is equals to 1 for some d and l integer. Suppose the GCD is 1, so you can write in terms of linear combination of elements in Z, right? So it means that because this, see, this is 0 because you are in Zm, so all the multiples of m, this is going to be 0. This means that this is 1, right? So this means that a is a unit, right? So this means that I have taken a here, I've got the 8 here. That means that u of m is contained in u of Zm. So this and this you will get the inequality. Okay, so I don't think this proof is very hard or something. If you get, if I give, then I think you can definitely able to solve. You can definitely able to write down the units, right? So that's it. And what else is here? What are the zero divisor? Okay, so if you have unit, then you can always find a zero divisor. The zero divisors of the ring Zm is all those a inside Zm such that a GCD of a comma n is greater than 1, because for 1, if this is unit, so what will be the zero divisor? This is greater than 1 because we have proved that a zero divisor cannot be a unit, right? Or a unit cannot be a zero divisor. So my choice is for 1, for equals to 1 we got unit. So for non-unit you can get, you will get the zero divisors, right? So these are the zero divisor. How many zero divisors are there? So Z of Zm, what is the cardinality of this set? See, we have total m elements, okay, and 0 is neither a zero divisor nor a unit, okay. Minus 1, minus I have to subtract the units because there are exactly 5m units here, right? See here, we have unit, we have to subtract my units. Also I have to subtract 0 because we by taking 0 we cannot do anything because 0 is neither a zero divisor not a unit. Okay, so this 1 is for 0 and total elements m minus 1 minus 5m means 5m are total units, right? So this, so I guess now I'm giving you a simple exercise. You take Z16 and find the zero divisors, find units and zero divisors. Find units and zero divisors, and I think this is very easy task I have given, right? So there is nothing special here. So what else I am left in? Let me see. Okay, yeah, so I do have some more special things here, so I have to complete. So what are product ring? Okay, so what I will define the product, okay, Cartesian product. So suppose R and S be two ring, R and S be two ring, two different ring, right? There is no need to something, and I will define then R cross S. What is R cross S? You know the Cartesian product R comma S such that R inside R, S inside S, right? So what will be the operation A comma B plus C comma D? This is actually A plus C b plus d, right? And a comma b dot c comma d, this is actually nothing but ac a dot c comma b dot d. Under these two operation, this r cross s is a ring. R cross s is a ring. Just a definition here. Now I am giving you to verify. I of r cross s, this is actually ir cross is. So I of r, that means idempotence of r cross s, that means r cross s is a ring, is actually idempotence of r cross idempotence of s. Okay, also this is 1, this is 2. Nilpotence of r comma s is equals to nilpotent of r cross nilpotent of s. Is it true? Verify. So I guess this second one is properly contained. So I guess this cannot be equal, I guess. So let me verify for the second one whether this is. So proof. How do we prove? Suppose x be an element of, that means nilpotent of r cross s is contained in nilpotent of r cross nilpotent of s, right? So suppose this is an element of r cross s. Okay, let me go with the if and only if condition. So this means that x is an some x1 comma x2, because r cross is a ring, x1 cross x1 comma x2 inside n of r comma s, r cross s, if and only if x1 x2 to the power k, this is actually 0 0 for some k, if and only if x1 to the power x1 to the power k, x2 to the power k is 0, if and only if x1 to the power k is 0 and x2 to the power k is 0, right? If and only if x1 inside n of r, x2 inside n of s. Okay, so here I cannot use the if and only if condition. You have to use x is x1 comma x2 inside n of r cross n of s. Okay, yeah, you cannot use here, you cannot use this inequality here, right? So have you got the point? So suppose I have taken one arbitrary element, because of the nilpotency to the power k is 0 0 and x1 to the power k, two coordinates are same if and only if the corresponding coordinates are same. So x1 to the power k is 0, x2 to the power k is 0. This means that x1 is inside n of r and x2 inside n of s. That means that x equals to x1 x2 inside. So this inside x1 inside. Okay, this implies that x1 okay, this is same, this is I guess, yeah, sorry. And so what I have got that n of r cross s, maybe the reverse is also correct, r cross s is contained in n of r cross n of s. This is also correct, I guess. This was also correct. Let me see you, let me prove. Okay, so this first, okay, yeah, prove that x1 comma x2 is an element of n. Now you take an element y for the reverse part, take y be an element of nr cross ns. Okay, so this means the y sum y1 comma y2. Okay, inside nr cross ns. Okay, that means y1 inside nr. This implies that there exists a k1 such that k1 is a natural number such that x1 to the power k is actually 0, and y2 is inside ns. This implies that there exists a k2 inside n. There is, this is also n such that x2 to the power k2 is 0, right? So you just have to verify that the y1 comma y2 will be 0 or not. So you just take y1 comma y2 to the power k1 k2. What it will be? It will be y1 to the power k1 k2, y2 to the power k1 k2, sorry, k1 into k2, right? This is actually 0 0, because y of k1 k2 you can write at y1 to the power, sorry, there is x y x, I don't y1 y2. So y1 to the power x1 is y1 to the power x1 is 0, y2 to the power x2 is 0. So this implies that y is in n of r crosses. This implies that n of r cross n of s is a subset of n of r crosses, right? So I am done with that, right? So this kind of things are somehow very useful for the competitive exams. So if you ask to find the idempotence of any product ring, so you just have to, how will you show? So you just compute the corresponding idempotence and then multiply it by partition product. That will be fine for you, right? So I guess this should be clear to you, right? So now what else is needed? What else I should teach? Yeah, there is one more, I guess. There is one more useful trick. After that we'll do some, these are some basic things, right? So I'm giving you one statement here and I will prove it. I will prove right now, I guess. Yes. Okay. Let m is a number which is actually some prime factorization p1 to the power alpha 1 dot 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 pk to the power alpha k. This is the prime factorization of the number. So then for zm, then zm is isomorphic to zp1 to the power alpha cross zp2 to the power alpha, p2 to the power alpha 1, p1 to the power alpha 1, p2 to the power alpha 2 cross this at a Cartesian product zpn to the power alpha n, right? Sorry, pk to the power alpha k, pk to the power alpha k, right? So zm is isomorphic to z of, for this, right? How will you show? Proof is very, I guess, easy. So you just have to define homomorphism. So I have since I have not defined homomorphism yet, so I'm leaving the proof as an exercise. So see this as a ring, right? Not as a group. proof. How will you prove it? F is a map from Z of M to suppose this product by Z of pi to the power alpha I is from 1 to k. Okay, how will you define f of a is goes to a mod p1 to the power alpha 1 a mod p2 to the power alpha 2 dot 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 a mod pk to the power alpha k. Okay, so you can verify this map is going to be 1 1 as a bijective homomorphism. Bijective homomorphism. So this means that this Zm is isomorphic to the product Z pi to the power alpha I is from 1 to k, and this is actually this is nothing but this quantity. Okay, so that's it. Do you need any example? I can give you the examples. I can give some examples here. So just yeah, so what kind of example I should consider? Suppose you have a ring, find the idempotence of Z50. So Z50 is isomorphic to, you know that Z2, so 50 can be written as 2 into 5 square, so Z2 cross Z5 square, right? How many elements are in idempotence of Z50 is actually idempotence of Z2 cross idempotence of Z5 square, sorry, Z2 means, yeah, Z2 means Z2 cross Z5 square, 5 square, right? So what is idempotence of Z2? Idempotence of Z2 is actually 0 1, and idempotence of Z5 square is actually also 0 1. That you can verify, right? So there is only 4 idempotence. In fact, any idempotence of Zp power k is 0 and 1. You can verify. Okay, okay, so there is 2, I guess there is 4. There will be 4, right? There will be 4, that's it, right? So in general, I'm giving you one statement, one is useful statement. I of Zm cardinality is actually I of Z p1 to the power alpha 1 cross dot 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 cross that means the cross will be somewhere here, right? Cross dot 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 cross Zpk to the power alpha k. Okay, I is here, this all are in subscript, which is actually I of Z p1 to the power alpha 1 cross dot 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 dot, dot cross I of Z pk to the power alpha k, right? This is actually some 2 ki power k. Is actually 2 ki power the number of distinct prime divisors. Right? suppose for here 2 to the power, how many distinct prime divisors are there? There is 2 and 5. There is 2 prime divisors, so 2 to the power 2 will be there. There is 2 prime divisor here, right? Suppose in Z51, and this statement is very useful statement, right? This is not in general. So this is number of. Suppose in Z51, you need to find the idempotence. So 51 can be written as 3 into 17, right? 3 into 17. So the idempotence I of Z51, the cardinality will be 2 square, which is 4, right? So this kind of examples are, so suppose in Z30, 30 can be written as 30. How can we write 30? 2, 3, 5. So idempotence in Z30 is actually 2. There is 3 prime divisor distinct, 8. Okay, how many 0 divisors are there? How many units are there? So units of Z30 is actually 530, right? What is 530? 530 is 2, 3, 4, 2 into 3 into 5 into half into 2 by 3 into 4 by 5. This is actually 2 cancel, 3 cancel, 5 cancel, 4 into 2 8, and number of 0 divisors is actually total number 30 minus 1 minus 8. Okay, so this will be something 21, right? So that is why this statement is very useful statement here. 2 की power के number of prime divisors, 2 की power number of prime divisors, because I of m, that means I, and Zm you can write is and Z p1 to the power alpha 1 cross dot. So this is same as I of, because I have proved here na, for 2 I have proved, right? Yeah, this is homework, very easy to prove, very easy to prove. Similarly for nilpotent I have proved, so you have to prove for. So anyways, so zk, and this is actually 2 की power k, that means in any z to the power pi to the power alpha I, any I have written here, right? zp की power k is only contains 0 and 1 as idempotence. There is no other idempotence except 0 and 1, right? So I guess this should be okay for you, right? So this kind of question might ask, and not so important. So I guess I am done with till now. There is boring thing, I know. Now from the next lecture we'll define something some interesting things. This are, I know there are boring thing. I also don't like this kind of things. So we'll discuss from the next lecture some important things and the structure of some important things and the structures of some things, and I will later on will define what else I need to define. I need to define many things, right? So there will be many lectures on ring. I will have to define the characteristic of a ring. After that I will define ideal, then we will move to prime ideal, maximal ideal, and it will move to principal ideal domain, PID, UFD and ED, and then we will move to irreducibility and Chinese human death theorem we do have, right? So that will be our course structure. Okay, so yeah, I think that's fine for today, and we'll meet tomorrow. Sorry, I guess we'll meet. Okay, that's it. Thank you.